So autoencoders, like we said, this is just the neural network version of dimensionality reduction. One can think of this as a kind of a nonlinear PCA, things that can find nonlinear surfaces along which the data is compressed onto. And here's how it works. Say we have 1,000-dimensional input. Then the question is, can we represent it well with just 10 numbers? We know that we can do it with PCA if it's possible, right? If the data mostly lies on a 10-dimensional plane in this 1,000-dimensional space, then PCA can discover that. But if it's a 10-dimensional curved surface somehow, PCA will just perhaps find a linear approximation to it, or maybe just totally fail. But we can do a nonlinear approximation of the surface by using this thing called autoencoders. And here's how it works. Okay, let's say for concreteness, we want to reduce a 1,000-dimensional space to a 10-dimensional sort of data input, data size. We create a neural network that has this kind of architecture, where you have an input layer with 1,000 numbers, and then we have a few layers with fewer and fewer neurons. And then we have a layer with 10 outputs, so really small layer. And then we have a few layers with more and more neurons. And then the final layer having 1,000 neurons again, output layer, okay? This is the input layer, this is the output layer. The weights and biases of the intermediate layers are unknown. And we try to solve for them and solve for them in a manner that output is as close to input as possible. Okay, so that's the idea. We try to, for instance, minimize output minus input squared, basically mean square error between output and input. So what does this accomplish? What it accomplishes is if, for instance, we find a network with this sort of bottleneck of 10 neuron layer, and we're able to get like train weights and biases in a manner that the output can be pretty close to the input with this kind of neural network structure. What that means is that these 10 numbers are able to approximate the inputs pretty well, because you can extract or reconstruct the output from just these 10 numbers. Okay, so that's the basic idea, very simple idea. The first part of the network is called the encoder, which is basically the compression part, right? So you take the 1,000 numbers and convert that into 10 numbers. And the second part is called the decoder, which is the reconstruction, which is also something that we did in PCA, which is taking the 10 numbers and then reconstructing the original image or whatever it may be, original data set, okay? So if we can find a neural network like this, then you can use the first part for the compression, namely converting the 1,000 to 10. And then if, for instance, we want the 10 to go back to 1,000 numbers, we can use the second part, okay? And that's it. And we can look up a MATLAB demo that does this pretty well. So that's one way to do nonlinear PCA. These words are just explaining what I just explained in words. Another sort of nonlinear PCA method is what would be called piecewise PCA. There's also something called kernel PCA, which I think does nonlinear PCA as well. I suppose autoencoder would be considered a nonlinear dimensionality reduction method. I do think it's a generalization of PCA to nonlinear spaces, although not perhaps everyone thinks of it like that. Piecewise PCA works like this, where you have some data set, and maybe you cluster the data into 5 or 6 groups, and then do a PCA for each cluster, and you get basically a few pieces that piecewise approximate the whole um, data set. So that would be another way of doing nonlinear PCA. In any case, so there are these nonlinear methods that go beyond just PCA, which is, as we saw, just based on linear algebra. I wanted to make sort of one last remark. So PCAs, I guess, have been very old technique. It's kind of fun to do PCA for phases, and the principal components for phase-like images have been called eigenphases, like eigenvectors. So I suppose these are a few principal components, supposedly. Okay. People did eigen sort of decompositions of data from worms slithering on surfaces. This is a worm called C. elegans, which is one of the most commonly studied organism in biology, neuroscience, and the shapes that this worm takes, they called eigenworm, which are just the principal components. If you take data for worm shapes and do a principal components of that, the first three principal components explain most of the data, and we can call people have called that eigenworm, just for fun, I suppose. And I think in your homework, I've given you data from a person running from one of my own papers, and you can do principal components analysis of a person running to reduce the dimensionality of the data. I think you can go from 50 dimensional to about 5 dimensional and retain maybe 90% of the data variance. Okay, so that's about dimensionality reduction, and that's about unsupervised learning. The next lecture is going to be about reinforcement learning.